Hello there, students. Today, got a special little demonstration for you. Kind of cool, right? So what I have here, in case you guys aren't aware, haven't seen these before, I have a ultraviolet lamp. You can do some pretty cool stuff with these. It's kind of neat. And we'll talk a little bit more about how these work. Is that certain objects, and I mostly only have something, but there's also other stuff that will glow even cooler colors, but they'll glow with like this extra kind of bright color. So like my teeth look super cool. We'll talk a little bit more about why that is as we get through the day, but that's going to be one of the goals that we're looking at, is why does something like that work? What exactly is going on in this scenario? So to recap a little bit and refresh and review where we've been, we know we've talked about electromagnetic waves, these including visible light. They're created when we have a charged particle that accelerates. Okay, there's a wide spectrum of these kind of electromagnetic waves. They have different wavelengths and frequencies, but all at the same speed. And then we can use these waves to transmit or receive information and or energy, right? Waves are a transfer of energy. It's just pure energy. That's what a wave is. So don't have any mass, it's just energy, and those waves that have higher frequencies can carry or transmit more energy. Okay, so that's what we know. And what we're going to be talking about today, and the big questions are, how can we get charges to accelerate, right? So how can we do that? What are the different ways to produce these different electromagnetic waves? And then how can these waves transfer energy to other things, okay? So we're going to talk about the creation of these waves specifically, and then how they can transfer that energy. And this is going to kind of wrap up our discussion on this big idea. Okay, about how we get these electromagnetic waves and how they can transfer energy. So let's start with this, right? The big kind of topic today is emission and absorption, emission being the creation, absorption being the reception of that energy, right? So how can we make these waves? There's three basic ways we can do it. The first way is we can accelerate an electron, okay? And this is kind of what I've talked about before. If we have a particle that's accelerating, a charged particle that's accelerating, we get an electromagnetic wave. We get this disturbance in the electromagnetic field. So one way to do that, to create something like a radio wave, right, is we could take a small charged particle like an electron, okay, and as we know, if we have like a wire, for example, we can, by applying a voltage to that wire, right, we can get that electron to move in one direction. So here, if this is the positive end of the wire and this is the negative end, the electron's going to move this way. It's going to move to the left. Now, if I reverse that, right, so if I have an alternating current, if I reverse the direction of that voltage field, I can get the electron to move the other way. So if I reverse this current at a certain frequency, right, then I can get a radio wave, right? A charged particle that is moving, accelerating back and forth. It's just like that marble oscillating up and down on that spring is what we have here in a wire. And so that's how you can get like a radio wave. Pretty straightforward, right? And radio waves have a particular frequency, so you need to do it at that frequency to get that. Microwaves, I was doing a little bit more research into these and how they work. They use something that's called a magnetron inside to create these microwaves, but essentially what you have is you have an electron that's spinning inside this kind of circular chamber in the presence of a strong magnetic field, and this creates some resonant electromagnetic waves based on the movement of that electron and the shifting of that magnetic field based on the movement of that electron. So once again, an electromagnetic wave, it's just this alternating electric and magnetic kind of field. And so where we have this electron that's moving, we have this magnetic field, and with that magnetron, you can actually create an electromagnetic wave in that way. Okay, so we have an electron that's moving. We're kind of moving it using magnetism, using electric fields, electric and magnetic fields. Okay, so that's one way. It's kind of cool. A similar way, but it's a little bit different, is like what we'd get to make an X-ray, for example. Okay, in the case of an X-ray, once again, we kind of have some free electrons, like in the magnetron. These are also similar to like what was used in like cathode tubes, which were used in like old TVs to like make moving pictures and make lights on a screen, right? But we have these free electrons that are given off by a material, and we have them in a strong electric field. So they move away from the positive end and move towards the negative end, and they accelerate as they do that. They speed up, right? So they get moving really fast, and all of a sudden they have a material here, right? Usually going to be copper in that case, where they hit it, right? Those electrons hit it, and they essentially come to a sudden stop, right? So if they have a high velocity and they have no velocity, then that is a big acceleration, right? That sudden slowing down. And that acceleration, that extreme acceleration, gives off X-rays, right, which have a very high frequency and a very short wavelength. Okay, so that's kind of three ways that we're looking at, and we kind of talked about this before. Is if we just accelerate an electron, okay, we can get a different type of electromagnetic wave. Now, the second way, option 2, and this is going to be the main focus on today, is a little bit more exciting, right? Option 2, the second way to kind of generate an electromagnetic wave is to excite an atom, right? So if we have an atom, this is just going to be a very generalized view of an atom. It's very simple. It's not drawn to scale, okay? So don't think it's drawn to scale. It's also, I didn't include all the electrons. I just included one electron. So here we have the nucleus, right, with a certain number of protons and neutrons, and then we have a certain number of electrons, usually the same number as the number of protons, that are orbiting in these shells, okay? Now, one thing to note is that there's different kind of electron shell configurations that you can have, right? So these electrons are going to be wandering around the nucleus, but they're not confined to just one shell, right? They can wander between these different shells. However, there is a shell that they tend to prefer in what's called their low energy state, okay? So this here, in this case, this electron would be in its low energy state, okay? So it's kind of steady, it's calm, right? But, so atoms normally exist in their lowest energy states, right? But if we have this atom gaining some energy, so if there's some energy that's being absorbed by the atom in some way, right? The energy could be in the form of heat, or it could be in the form of another excitation, which we'll talk more about later, right? But if that atom absorbs energy, right, then what will happen is that in order to kind of take hold of that energy, in order to hold on to it, this electron will actually jump up into a higher shell, a higher energy shell. Okay, so we'll jump up into a higher energy shell, and essentially that means that the electron is, or that the atom is in a higher energy state. Okay, it currently has more energy than it had before. It's absorbed it. And the energy is kind of stored in this electron being in a farther out shell. Now, one thing of note is that the electrons, and it's not always just one electron, it's like multiple electrons in an atom that are doing this, depending on the amount of energy that flowed in, right? The electron is not particularly happy up here. It's not totally stable. It's only partially stable in this position. It can't really stay there for that long. So what's going to happen is that eventually, right, the electron is going to drop back down to its lower energy shell, and it's going to kind of lose that energy in the process. Say lose because we remember conservation of energy. It cannot be created nor destroyed. So that kind of lost energy is actually just radiated off as an electromagnetic wave, right? Now that electromagnetic wave has a specific energy level, right? And we can kind of call the electromagnetic wave, you'll kind of see this term, we call it a photon, which is kind of like a little bundle of energy that kind of travels in this wave-like function. It's essentially just a wave, but sometimes you'll hear it when we refer to as a particle or a packet of energy. You'll hear the term photon, so I just wanted to introduce that. Okay, but to refresh, okay, so here we have this atom. It's just kind of chill, it's happy. Energy flows in, right? Because of that energy, the electron jumps up to this outer shell, right? It's not particularly happy up there. It wants to kind of get back down to its lower shell. So when it does finally fall back down to that lower shell, it gets rid of some of that energy by emitting an electromagnetic wave. And that wave has a specific energy level, right? Well, that energy level, we have a higher energy state here, a lower energy state there. There is a specific change in energy, right? A specific amount of energy difference between these two states, okay? That is the energy level of the electromagnetic wave. Okay, each wave frequency, right? Each electromagnetic wave has a specific energy level. Okay, so the exact frequency of the electromagnetic wave that's emitted corresponds directly to the change in energy between the two states, between this high energy state and the low energy state. Just to throw out some numbers, and these wouldn't actually be numbers that you'd see, but let's say in the higher energy state, right, this atom kind of has like 5 joules, right? In the lower energy state, it has 3 joules. Right, well, what's the difference in energy between those two states? 2 joules. Okay, so the electromagnetic wave would have 2 joules of energy. Okay, so now energy for a electromagnetic wave is proportional to frequency. As we kind of mentioned, it's the more kind of wave crests that are going by per second, the more energy that wave has. And specifically, there's actually an equation that we can use, which is this, and this is one that you guys will need to know. The energy, right, carried by a wave is equal to Planck's constant, which we represent with this number h, times the frequency of that wave. Okay, so each wavelength has a specific frequency, right? And therefore it has a specific energy. And that amount of energy in joules is equal to the frequency times Planck's constant, which is 6.6 times 10 to the negative 34th. It's a very, 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 very small number, okay? So that's the amount of energy that a specific wavelength has, right? And so when we excite an atom like this, right, the difference between these high and low energy states for each electron determines the wave, right, the electromagnetic wave that is emitted by that electron, okay? And usually it's going to be a particular color, right? It's usually within either the infrared, the visible, or the ultraviolet wave spectrums, right? So in a lot of cases, when this happens, we can actually see them, okay? Now, because all atoms, every single atom has a unique electron configuration, okay? So, for example, hydrogen has one proton, one electron, and that electron can exist in certain states, right? Helium has 2 electrons, right? Those electrons can exist in certain, like, kind of certain shells in certain states, right? And each atom, right, with its varying number of electrons, have these unique configurations, these unique shells that they can jump up and down between. And so each atom will emit a specific set of frequencies, right? And we call this set of frequencies that they emit, right, that they're kind of limited to, their emission spectra. It looks something like this, right? This is an example atomic emission spectrum for some different metals. Here we have beryllium, copper, manganese, strontium, titanium, right? And these little bars represent kind of the color of visible light and this corresponding wavelength, right, that they end up emitting, right? So if I heat strontium, for example, right, if I excite it, right, its electrons, right, can jump back and forth between these kind of specific energy levels corresponding to these wavelengths, right? So strontium, when it's excited, can emit these wavelengths of light through this excitation process. Okay. Now, one of the reasons why this is kind of cool and important, there's a lot of reasons. This allows us to actually like identify like unknown kind of elements. If we have like an unknown kind of element, right, an unknown emission spectrum that something is giving off, right, we can match it, right, to an existing one that we know that we've measured. We can say, hey, this unknown thing is probably strontium. Okay. This is super useful for figuring out the composition of like stars, of things that are far off, even of like smaller things. Just knowing kind of the light that they give off when they're excited, we can identify what they are, which is really cool. Now, like I mentioned, this is also exciting because in the case of something fun like fireworks, right, where we have all of these different colors, right, that are being kind of produced in this dazzling light display, right? Well, how do we get these specific colors? It's not like there's like a lens or a filter or a gel up there, right, that's giving them those colors. They're actually being produced and emitted and coming into our eyes and being picked up by our eyes, right? Well, if we actually look at how you make a firework, right, what you end up getting is that the different colors correspond to different elements, right? Usually different metals that are found in small, fine, powdery bits, right? They're called metal salts. And you see those different colors, and they're in those fireworks. And when they explode, right, those the atoms get excited, and they emit and they release wavelengths of light that are of a particular frequency, of a particular color, right? So strontium, for example, is used to make these kind of bright red fireworks. And if you guys want to see this in action, it actually looks something like this. You can just do a flame test. So here they have some strontium chloride salts, right? So it's very kind of fine little particles of strontium mixed with kind of chlorine. And when you add it to a flame, right, the flame turns this bright red, right? And that's because those strontium atoms are getting excited, right? Their electrons are jumping to kind of their outer shells, right? And then as they fall back down to their lower shells, they emit red light. They emit a wavelength of electromagnetic light, right? Electromagnetic waves that are in the red light wavelengths, right? So that's what we actually see, is we see this bright red flame, right? It's really pretty cool. And then as the strontium kind of vaporizes and leaves that system, then the flame kind of returns to being normal, okay? But it's really, really kind of something. So that's how we end up getting fireworks. It's all due to this whole idea that each atom has a unique kind of emission spectra based on how their electrons are jumping out and back between these shells, right? And the energy level difference between those shells determines, right, the frequency that we end up with. And the frequency determines the electromagnetic wave that we have. Okay. So one last thing of note that I want to bring up with this is if we have something like this light bulb, for example, right, which produces this nice kind of soft glow. Let me hit the lights again using my special light stick. Ah, there we go. Nice light stick. Okay, so if we get this nice, and you guys remember playing around with this, so we get this nice kind of glow. Now this is an incandescent light bulb, right? Here we have this tungsten filament, right? Tungsten being a specific element, right? And therefore tungsten should have, and tungsten does actually have its own emission spectra. It has a different frequency of lights that it can produce when it's excited, right? As its electrons jump back and forth between those shells. Now, this color that you guys see here is not actually the emission spectra of tungsten, right? This is what we'd call a broad spectrum. This is what we'd call white light. So this is giving off kind of all the colors simultaneously. And the reason why this is, and why it's not just that of tungsten, is because if we have something like this that's solid, okay, where the atoms are packed in there more tightly, then the waves, those electromagnetic waves that are created, kind of interfere and combine and interfere with each other to actually give off a continuous spectrum of white light. So we're actually getting all the colors together in here. Okay, the same kind of thing happens in the sun, and this phenomenon is referred to as incandescence. Okay. So in order to get emission spectra, like we get in those fireworks, we have to have those kind of atoms that are essentially vaporized, right? They're spread far apart and they're not tightly packed next to each other, so they can really emit those colors that we end up seeing. Right? If we have them close together with each other, then they end up kind of giving us this nice kind of incandescent glow that is all the different colors combined. And there's kind of a great example of a little piece of that reading in the book. If you guys kind of check that out if you're more interested in that. Let's hit the lights. Boom. Okay, so that's option number 2. Okay, we can excite an atom. So number 1 is we can just physically kind of move, either using electricity or magnetism. We can use that to move an electron. The other way is if we just excite an atom, right? If we put energy into it, either heat or other energy is absorbed, it's excited, then it will actually emit, right, electromagnetic radiation. Right? It'll emit these wavelengths. And typically these, right, we're looking at infrared, visible, and ultraviolet, right? In a lot of cases is what you get from that. And then the last option that I want to talk about is you can actually excite the nucleus. Now I bring this up because this is how we get things like gamma rays, for example. So similar to how electrons can have higher energy configurations and then they can have the lower energy states, a nucleus and the arrangement of neutrons and protons is the same, right? So a lot of times after a nuclear reaction, when we get atoms that are splitting or fusing, sometimes those atoms in the nucleus, the protons and neutrons will be in one configuration and they'll have a higher energy. They're not necessarily stable there. And then they'll kind of like rotate and shift and get into a lower energy configuration, right? And when they do that, they give off actually a gamma ray, right? They release the change in energy levels between these states is so high, right? It's so much greater than that for an electron, right? That they actually give off a gamma ray. Right, which is kind of interesting. So these come off of like stars that come off of after like uranium reactions. They are naturally occurring, and they can be, as you guys know with gamma rays, they can be actually quite dangerous. Okay, so this is the third way. So we can either, right, physically accelerate that electron using electricity or magnetism. We can excite an atom, right, to get it to emit an electromagnetic wave, or we can excite a nucleus to get it to emit like a gamma ray. Okay, now all of these things are happening in stars, and that's why they emit such a broad spectrum of electromagnetic radiation, right? Those waves also tend to interfere, and so we get this whole spectrum of different waves that can be created. Now, the second question that I wanted to talk about and address is how can these electromagnetic waves transfer energy to matter? So now that we know how they're kind of created in those specific ways, so we can create electromagnetic radiation, how can they transfer that energy to other things, right? How can we read those signals? How can they like warm us? How can they allow us to see things, right? How does like this work, right? So that's the last piece that I want to kind of talk about. And so let's go back to the idea of our tuber right here sitting in our electromagnetic wave. I've got here 3 electromagnetic waves that they're sitting on, right? One is kind of like this long, languid, very big wavelength, low frequency wave. One is a little bit more shorter wavelength, medium frequency, and one is a high frequency, short wavelength wave, right? And here we have a tuber. Now, depending on the type of atom or molecule or particle that this tuber is, right, they will be able to respond differently to the wave. Right? You can kind of picture what might happen in this case as this wave goes by. Right? The tuber might even not notice because the wave is so long and languid. Right? In this case, right, you could picture our tuber here. It's like they're really going to feel themselves going up and down and up and down and up and down. In this case, right, this wave might be just so violent that it actually tears the tuber to shreds, might even knock them out of their tube, right? So thinking about that, and if I had a different tuber, let's say that I had a really, really, really big tuber, right? Well, what's going to happen with that, right? What are these kind of things going to do to my tuber? What if I had a really, really small tuber, right? How is that going to affect things? So that's the idea here. If we could imagine, right, this one might not even be noticeable, right? This one, they just go kind of up and down, and this one, they might even get knocked out of their tube, right? Depending on the frequency of those waves, and therefore the wavelength of them, this tuber is going to be able to absorb that energy or respond to that energy differently. Okay, so let's talk about some different examples. Sometimes that energy is just reflected back or passes by, right? This is in the case of, and it's not necessarily like absorbed, this is in the case of like radio waves passing by us. In a lot of cases, it's just reflected back off of our bodies, or sometimes they just pass right through us, right? And that's because these waves aren't really operating at a scale that can affect our molecules and atoms, right? They're just so large scale that it doesn't really do that much, right? But in a lot of cases, right, that energy can be absorbed. Okay. So if that energy is absorbed, if it is actually transferred and it's not just reflected back or passed through, right? If it is actually absorbed and there's some kind of reaction, then a lot of times, right, it ends up being re-emitted, right? So I know in one of the first, or I think it was the second reading that you guys did, the most recent one, they talked about kind of transparency, how when light kind of moves through glass, right? Visible light, for example, kind of it's absorbed by those glass molecules and it's passed on to the next glass molecule, and it's passed on to the next glass molecule until it gets to the end, and then it's passed on and continues kind of through space and through the air, right? So that's one example where the energy can be absorbed and then kind of passed along. Okay, this would be like with our tuber, it'd be like, let's say a wave comes along, it kicks our tuber up in the air, they go up into the air, and then they fall back down, and they create a wave, right? That was just like the wave that knocked them up into the air, right? Sometimes this absorbed energy just makes it vibrate a bit more, right? So this energy is, in this case, it's absorbed as heat, right? This is like infrared energy, right? So this might be like this guy, right? This guy in blue, right? The tuber vibrates up and down, and so they start to kind of heat up, right? And then you can imagine, like, if all of a sudden this wave passed and the water was calm, they might still be vibrating. The tuber might still be vibrating, so they're actually creating waves of their own, infrared waves of their own. This is why, like, when I go out into the sun, for example, and I'm laying there in the sun, the reason why the sun kind of feels warm on my skin is because of that. Those infrared waves are coming down, right, and they're causing the molecules that make me up, right, and specifically the water is the big one that they really affect. But they cause those molecules, right, mostly water, to vibrate just a little bit more, kind of like in place. Right, so they give them heat energy, and even after the sun's gone, right, I'm still going to be radiating out that heat energy a little bit. Okay, and so in that case, it's like it's kind of passed along, but it's kind of like delayed, right? It's absorbed and then it's kind of passed along later, and that's infrared wavelengths. Okay, sometimes the energy coming from an electromagnetic wave can make things rotate. So, for example, in the case of a microwave, this is really cool. Microwaves work by heating up water molecules in your food, as well as some other types of molecules, but these molecules have to be polar. That's because these molecules kind of fit within these microwaves pretty nicely. The microwaves are pretty big and the atoms are pretty small. But because of the scale of things, and this is not to scale at all, right? These molecules will be incredibly smaller compared to these waves. What happens is as these waves go by, because water is a polar molecule, it has a more negative side and a more positive side. And because of the relationship between electricity, right, and electromagnetic waves, and what happens is that these water molecules kind of orient themselves to face the wave in a particular direction. So what you end up getting is that the water molecules end up rotating and spinning, right? So it's just like kind of the infrared where they vibrate a little bit more, except for even more so, right? So this can actually get water quite warm quite quickly, so much so that it can heat food, right? And that's because the water happens to be polar. Sometimes when that energy is absorbed, it's re-emitted as a different wavelength, right? So going back to this guy here, right? The reason why my teeth can kind of glow an extra shade of white is because they, right, this lamp is actually putting out ultraviolet radiation. And there's actually this whole process with how it works in this, that this lamp puts out ultraviolet radiation, ultraviolet waves. And that actually has to do with excitation of the atoms in here. It's actually mercury atoms that get excited. And they emit kind of harmful ultraviolet wavelengths. But those are absorbed by the coating here. And the coating here then absorbs those kind of harmful ultraviolet waves, and it re-emits them as a different wavelength, slightly less harmful ultraviolet waves that are kind of on the near ultraviolet spectrum. And it also gives off a little bit of like a purple. Like there's a few kind of indigo and violet waves that are also given off of that wavelength. And then this ultraviolet, and it's that ultraviolet wavelength then that is absorbed by my teeth and the molecules that are in my teeth, molecules that belong to a class called phosphors, because they can phosphoresce. And those, right, those actually absorb, right, the ultraviolet radiation, and they emit kind of like a light white color, right? A broad variety of different wavelengths that we see as like this bright white, okay? So that is all having to do with that excitation and then re-emitting, okay? And we call this kind of phenomenon fluorescence. And this is everywhere. It's like this happens all the time. Things will fluoresce, they absorb, and they kind of re-emit as a slightly different wavelength, right? They don't pass along perfectly. They kind of re-emit it just slightly changed. And sometimes that energy is absorbed and makes a molecule change its shape. So fun fact, this is how your eyes actually can pick up color. Is they have, you have molecules in your retina that are called, I think they're called rhodopsins or opsin molecules. And what they do is as certain wavelengths of energy come in, they actually make those molecules change their shape, right? And in the changing of their shape, they kind of send signals to our nerve system to say that, hey, that we've seen a particular like color, right? So that's kind of cool. Sometimes the energy is, and this is a big one, is absorbed and it breaks or makes chemical bonds, right? So when we think of things like cancer and mutations, things as simple as like sunburn, right? What's actually happening here, and it's kind of similar to this scenario, right? Where because of the size of our tuber, which is essentially an atom or a molecule, really a molecule in this case, those waves, the wavelengths are short and they're high energy enough, they can actually break apart, right? They can knock our tuber off of our tube. They can break apart those molecules and cause things like mutations. They can cause like sunburn. Can lead to things like cancer. And so these are bad, and they typically happen with small wavelength high energy waves, ultraviolet, especially far ultraviolet, UVC, UVB, X-rays, gamma rays can definitely do these kind of things and can cause some serious harm because the size of those wavelengths, right, really fits in and can break apart those molecules. Similarly, sometimes that energy with those short wavelengths can actually free an electron from an atom, right? So if you have atoms that kind of have electrons that they aren't holding on to too tightly, they can, when they're hit by these wavelengths, they can knock free an electron. So this is kind of cool. And then sometimes the electron can move electrons in a conductor, or sometimes that energy. So if we have like radio waves or like microwaves, far microwaves, for example, they can, if we have a conductor, like a receiver, like the antenna on your car, right? The electrons that are in the antenna kind of get moved, right? Because of this radio wave, this alternating electric and magnetic field. And so then your car can essentially read the kind of movement of those electrons, generates like a current, and then it can use that to actually power a speaker at a certain kind of frequency, and then you hear sound, right? So you can actually hear the signal that's being produced there. So And that's, once again, kind of getting up there to like option 1 about how we can, by moving these electrons back and forth, it can create a radio wave. Similarly, a radio wave can then move these electrons back and forth when it's received, right? So a lot of these have to do, a lot of how these work also have to do with how they're created in the first place. So essentially, if I reverse any of these, right, if I reverse option 1, if I reverse making a radio wave, I can use a radio wave to do this same thing, right? I can use a visible light wave to excite an atom, right? Or I could use a ultraviolet wavelength to excite an atom, or I could use an infrared wavelength to excite an atom, right? And it can jump up there, and then it can re-emit that wavelength, okay? So it can kind of pass it along. And similarly, I could use a gamma ray to excite a nucleus, right? And this can actually happen, okay? So that's how we can transfer energy to matter, right, using these electromagnetic waves. And it, gives us all sorts of cool kind of things that we see and observe in the world, and kind of explains how electromagnetism kind of works to function as a transfer of energy, right? So hopefully you guys have a little bit of better idea as to how electromagnetic waves are created and how their energy can be transferred to other things. I'm remembering some cool things like black lights, like fireworks, thinking of that, as well as just like how we create radio waves and x-rays and things of that nature. You guys' homework, there's a little simulation I'm going to post, which actually has, you can mess around with some different wavelengths of lights. You can turn on and off this flashlight, right? And you can select some different molecules and see how they actually respond, right, to these different wavelengths. So here we see carbon monoxide. As this microwave comes in, carbon monoxide is polar, so it actually rotates and it spins. Similarly, like I was talking about with water, right? We can see as the microwaves come by, water is able to spin. Kinetic energy, it heats it up, right? And it also re-emits those microwaves in its own time as well. So I'm going to have, I would like you guys to mess around with this. I'm going to have some guided questions that you guys need to fill out. And please don't cheat, just a little note. I know sometimes it's easy, like with this digital stuff, but just don't do it. So next, we'll be doing some wave practice calculations, and then on the horizon, we'll talk a little bit more about color, reflection, refraction, mirrors, and rainbows, and cool stuff that we can do with light waves to allow us to see things and perceive the world as we do. So thank you guys for tuning in. Sorry if this was too long, and I will catch you guys later.